In this next segment, we'll look a little bit more at some of the details of blood cells, and then related to this, we're going to talk about the mechanisms of blood clotting. So antigens, just a general term here that I want you to be aware of, because these are molecules that are found on the surface of cells. Usually they're proteins, but they could be carbohydrates as well, but typically these are proteins. And these help our immune system recognize ourself. And so our immune system is trying to detect foreign molecules as a potential foreign invaders, such as the molecules that are on the surfaces of viruses or on bacteria. And they recognize that those cells aren't our own cells, and they then produce antibodies. These come from lymphocytes, and then these attack those foreign invading molecules and help to kill off bacteria and viruses. But this leads to something referred to as the ABO system. These are antigens that are on the cell surfaces of erythrocytes, on red blood cells. People who are type A have the type A antigen on their red blood cells. People who are type B have the type B antigen. People who are AB have both of these antigens, the A and Bs. And people who are type O don't have either of those. Okay? So this is called the ABO system. So this is important because people who are type A have type A antigens, but they have B antibodies in their plasma and floating around in their bloodstream. And people who are type B then have the type B antigen on their red blood cells, but they have type A antibodies, anti-A antibodies in their bloodstream. People who are type AB, they don't have any antibodies because they have both A antigens and B antigens, and so they don't need, there's no mechanism for them to form these antibodies. And then people who are type O don't have either A or B antigens, and as a consequence, they have both anti-A and anti-B antibodies. As we'll see, people who are type AB are universal recipients for blood transfusions, and people who are type O are universal donors. And so what this is about is this transfusion reaction. What happens is if you receive the wrong blood type, the antibodies that are in that person, in the recipient's bloodstream, will attack the donor's red blood cells and cause them then to coagulate, to agglutinate and form clots. So here's an example of this. So here's somebody who's type A, and they have type A antigens, and they have type B antibodies in their plasma. Somebody who's type B has type B antigens, and they have type A antibodies in their plasma. So if you give somebody who is type B, type A blood, this will cause their type A antibodies to bind onto this and coagulate them, agglutinate them, destroy them. Same thing with type B going into somebody who's type A, and these will then agglutinate as well. This is dangerous, extremely dangerous, potentially lethal to put the wrong type of blood from the donor into a recipient. So it's very, very important that they do blood testing to see if you're ABO or AB before you do a transfusion. There's another antigen that's called antigen D, more commonly referred to as the Rh factor. So someone who is Rh positive has the antigen, and someone who is Rh negative doesn't. So often you'll hear somebody being A positive or B positive or O negative. That second part of that negative positive, is referring to this Rh factor. This is important in pregnancy because if a Rh negative mother has a Rh positive baby, there is often a little bit of blood exchange, not usually during the pregnancy, but during delivery is a pretty messy process, and there can be blood exchange. And so what happens is the mother's immune system sees that Rh positive antigen and produces then antibodies against it. This can be really dangerous then if the next baby is Rh positive. So blood cells don't get across the placenta in any normal sort of way, but antibodies can. And so now the antibodies being made by the mother can attack the red blood cells of the Rh positive baby. This can lead to something that's referred to as erythroblastosis fetalis. And this will, at the very minimum, make this baby anemic, but it can be extremely dangerous, and I think even lethal in some circumstances. So what often will happen is if a Rh negative mother has an Rh positive baby, she will receive something called RhoGAM. And what RhoGAM does is it binds onto those antigens from the Rh positive, the little bit of Rh positive blood that got into her bloodstream. It binds onto those antigens and makes them invisible to her immune system. And as a consequence, she won't produce then antibodies against that Rh factor. So now let's look at blood clotting in a more of a normal sort of way. And this is referred to as hemostasis. And this is just blocking bleeding from a damaged vessel of some sort. And so when you damage the blood vessel, this exposes collagen. And the collagen then is exposed then to platelets, and we'll show you some examples of this further in just a moment. But this initiates then a rather complicated cascade of events. So one is vasoconstriction. You want to reduce the blood flow to injured blood vessels. Also the formation of a platelet plug. We'll talk about that more in just a moment here. And then the conversion of fibrinogen into fibrin, which then forms this web that helps to hold that platelet plug in place until that blood vessel has healed. So let's take a look at these platelets in a little bit more detail. The intact epithelium, endothelium, I mean, of these blood vessels release one of the prostaglandins we talked about in the last chapter called prostacyclin, and also releases nitric oxide. These together cause vasodilation, which is good for smooth blood flow. And inhibits blood clotting. And then it also helps to prevent platelets from getting sticky. And so the platelets don't want to aggregate then. This helps to prevent then forming clots in healthy, intact blood vessels. They also have this enzyme called CD39. And this helps to break down something called adenosine diphosphate into adenosine monophosphate. Adenosine diphosphate is something that also makes platelets sticky to each other and helps them to aggregate. So this helps to prevent that aggregation. Now, when you get a damage to a blood vessel, this exposes the collagen, and as I mentioned, the platelets then stick onto that collagen, and then there's a blood clotting factor called von Willebrand factor that helps to hang on to them further, keep the platelets from then drifting away. Platelets then undergo this cascade of events. They cause the recruitment of additional platelets by making them sticky and form this platelet plug. And so they release ADP. This helps to make platelets sticky. Serotonin, same serotonin we talked about in the central nervous system, but in this case it's working as a vasoconstrictor to help to reduce blood flow and reduce the loss of blood through a damaged blood vessel. And then again, one of these other prostaglandins, in this case it's called thromboxane A or thromboxane A2. And these help to make platelets sticky and also cause vasoconstriction. And then there's going to be a cascade of clotting factors that we'll discuss here in just a moment. So here's an example of what this looks like. So here's a happy, healthy blood vessel. Here's the wall of the blood vessel. Here's the interior of the blood vessel. And we're releasing prostacyclin, one of those prostaglandins, and nitric oxide to help to prevent platelets from being sticky and to cause vasodilation and smooth blood flow. And then here's that CD39 that's converting ADP into AMP and helping to inhibit then the platelets from getting sticky to each other. When the collagen is exposed from damage, then the platelets will stick onto that collagen, and then this initiates a very complex series of reactions. This releases a different prostaglandin, here called thromboxane A2, and ADP. These guys make platelets sticky and cause some vasoconstriction, and helps then to form that platelet plug. And then, as we'll see in a moment, there's also the conversion of fibrinogen into fibrin, which then falls on top of this here and makes this little fibrous net mesh that helps to hold this whole platelet plug in place. So let's take a look at that fibrin in a little bit more detail. So fibrinogen is converted into fibrin by two different pathways. One's an intrinsic pathway and the other is an extrinsic pathway. The intrinsic pathway is intrinsic because it's due to the activation due to exposure to the collagen. And it activates one of these clotting factors called factor 7, and it initiates a cascade of additional blood clotting factors, and I'll show you a diagram of that in just a moment. The extrinsic factor is initiated by a tissue factor called thromboplastin or factor 3. This is a little bit faster than the intrinsic pathway, and I'll show you an example of that as well. So here's a table showing all of these different clotting factors. I am not going to make you memorize these. You do need to know what clotting factors are, but I'm not going to make you memorize these. And this is a very unfortunate set of names. You will have to memorize these if you go on to med school, vet school, dental school, those sorts of things. Take this course at a higher level. You will be expected to memorize all these. But it's really unfortunate for a variety of ways. One is that these factors named 1, 2, 3, 4, 5, 7, 8, 12, whatever here, unfortunately don't have anything to do with the sequence in which they're activated. They are named in the sequence in which they were discovered. And then they got a bunch of other names like fibrinogen or prothrombin, some after the people who named them, a Stewart-Prower factor, Hagman factor, Christmas factor. So they have a whole variety of different names as well. And like I say, I'm not going to make you memorize these guys, but you will have to memorize these at a later section if you take a more advanced course on blood clotting. But for our purpose of our course, you need to know what blood clotting factors are, but not all of these pathways on here. So then let's take a look at this. So here are things you do need to know. So calcium and phospholipids, as you'll see in a moment here, are important to all of these pathways. And this helps to convert a precursor to thrombin called prothrombin into its active form, thrombin. And thrombin is the one that then converts fibrinogen into fibrin. You need to know this detail. There's also another molecule here that's important, vitamin K. This is needed by the liver to make the functional form of these clotting factors, and this is clinically used to inhibit this process to prevent blood clotting. I'll mention that in just a moment. But anyway, here's the different clotting pathways. And again, here's something you will need to memorize for later courses if you're going to take a more advanced material on these pathways. But let me tell you what you do need to know. There's an extrinsic pathway, an intrinsic pathway, and then a common pathway. You need to know that there are those three pathways, extrinsic, intrinsic, and common. But you don't need to know all these different steps. You do need to know that calcium and phospholipids are important in each of these different pathways. And then you need to know everything down from here. You need to know the prothrombin to thrombin. Thrombin converts fibrinogen into fibrin, and fibrin then forms these polymers that help to seal that plug. So that's the part of it that you do need to know. You do not need to know all of these different steps in between. Here, you will be expected, as I mentioned, if you take this at a more advanced level. So there are a bunch of different clotting disorders and anticoagulants, and some of this you'll need to know, others you do not. So mostly you need to know that there are clotting disorders. Some of these are inherited or genetic. You don't need to know the names of these, but these are different forms of hemophilia, and they have to do then with genetic defects in various different types of clotting factors, whether it's hemophilia A or von Willebrand's disease or Christmas disease. Again, it's a defect in these different clotting factors. You do not need to know these details. You need to know that there are inherited clotting factors that are genetically based. And then there are some that are acquired. So for example, you're not making enough vitamin K. As I mentioned, vitamin K is important for the formation of the functional form of a variety of clotting factors. And then there's a bunch of different anticoagulants. Aspirin, this is the most common one. And as you should remember from the previous chapter, this inhibits then the formation of prostaglandin. It's a COX inhibitor. And so as a consequence, then it prevents platelets then from being sticky. This actually is functional. And so for people who are at risk for clotting disorders like strokes or heart attacks, low doses of aspirin can sometimes be useful for that to help to reduce the stickiness of the platelets and the formation of clots. These are just baby aspirin, so there's a very, very, very low dose. But high concentrations of aspirin over long periods of time can result in bleeding disorders. People will bruise very easily, or if they get a cut, they'll have a very hard time for that wound to stop bleeding. There's also other kinds of drugs, coumarin, heparin, and citrate, that helps in various ways then to prevent clotting. Some of this is involved in inhibition of vitamin K. This is used clinically. Heparin as well is used in a variety of different kinds of things. This helps to prevent the formation of thrombin, and so you can't produce fibrin from fibrinogen. And then citrate and other chelators of calcium, like EDTA, then prevent the calcium being available. And as I mentioned to you, that's important in all of these pathways, extrinsic, intrinsic, and common pathways. So here's a little bit more about that. So one is, well, we need to get rid of these clots once we're done. And so these are dissolved by as yet another endogenously formed enzyme that's called plasmin. And this helps to break down the fibrin once that wound has healed, because you don't need that clot there anymore once the blood vessel has recovered. And then, as I mentioned, that relates to that last slide, Those are certain drugs that are used to help prevent clotting, as say calcium chelator, sodium citrate, or EDTA. So when you get your blood test, when you do a yearly physical, you'll take some blood from you and they'll put in some test tubes. Some of those tubes will have citrate or EDTA in it, or heparin in it to prevent the blood clotting, so that that blood in that test tube doesn't clot. Heparin, as I mentioned, blocks thrombin, and this is used clinically in a variety of different ways, but actually basophils and mast cells in our own bodies make heparin as well. And then Coumadin, as I mentioned, is also used clinically to inhibit vitamin K. And as a consequence of that vitamin K inhibition, this then reduces the ability of the kidney then to make functional forms of a variety of clotting factors.